Hello geometry students and welcome to section 1.2. Today we're going to take a delve into segments. We've already talked about what a line segment is, but we want to be able to do some actual math with it. So that's what today is for. Before we go through with today, I just want to talk about this vocabulary word here. This is going to become one of the most important terms in the entire class. A postulate is something that sounds crazy, but isn't actually that difficult. A postulate is just a rule that does not require a proof. So it's a rule that doesn't need to be proven for us to assume it's true. That seems a bit odd, so let me give you an example. One of my favorite postulates of all time, and one of the simplest, starts with a square. This postulate is called the right angle postulate. The right angle postulate says this: all right angles are the exact same angle measure. Boom, that was my mic drop. Yeah, it doesn't seem that difficult, right? I mean, we know that a right angle is just a 90-degree angle. And of course, if these are all right angles, then they're all 90-degree angles. We don't need to prove that every single right angle in the world is 90 degrees. We call them right angles because they're 90 degrees. So that's an example of a postulate. Another thing that you might have heard of before is a coordinate. In Algebra 1, you may have seen coordinates used on a graph like this. See, this is where graph paper comes very, very handy. Let's say I have these two axes, my x-axis and my y-axis, and I put a point right there. Well, assuming each of these squares is just one unit, you could very easily tell me what the coordinates of that point are. It's 2 to the right, so the first coordinate is 2, and it's 3 up, so the second coordinate is 3. That's the coordinate of the point. But in geometry, we won't always be using these graphs. I mean, think about it. This graph is essentially just a flat plane, a 2D object. Once again, we know it's 2 dimensions because it has 2 directions, an up and down direction on the y-axis, and a left and right direction on the x-axis. We also deal with one-dimensional objects and 3-dimensional objects. So if I gave you a one-dimensional object like this, and a point, let's say, right here on it, how could you get a coordinate for that? Well, it might help if I label this particular line, because this line has a very special name. I wonder if you remember what this is called from elementary school. This particular line is the number line. And so when we're talking about coordinates on the number line, there's only really one number tied to each point. So we don't need to list 2 points like over here. The coordinate is just 3. There's only one direction, it's left and right, so there's only one dimension. So you only need one number to describe a coordinate. That is the basics of what a coordinate is. But let's get a more formal definition, because we know in geometry definitions are everything. So, the real number that corresponds to a point is what we call that point's coordinate. It's the real number that corresponds to a point. For the example here, I'm going to once again just draw that number line we had before, maybe a little bit shorter for the sake of time. That would be my example right there. This would have a coordinate of just 1. When we label coordinates, we like to put them in parentheses, sort of like how you would on a graph. You can also just call them x1 or x2 or whatever sort of value you want to attribute to it. But most commonly, I'm going to be writing them as a number in parentheses, or if it's in 2 dimensions, 2 numbers in parentheses, x and y. Distance is, once again, another word that you all know, or at least you should. Let's go back to this number line that we have here. It's a beautiful number line, why not use it? If I put a second point here at -4, would you be able to determine the distance between the blue point and the red point? And before we do, I think it might even be appropriate to give these 2 points names, A and B, so that when we talk about them, we know which one I'm referring to. B for blue and A for a red point. Anyways, if we're trying to find the distance between these two, we can do it a couple different ways. We can count one by one. 1, 2, 3, 4, 5, 6. Oh, it's 7 away. The distance between those two is 7. That was easy because we have points that are really close together. I mean, -4 and +3 are not that far apart. If I had asked you to find the distance between a point with triple digits in the negatives and triple digits in the positives, we might have a problem. So we need a more formulaic way of understanding distance and for writing distances. The distance between points A and B, the distance between points A and B, which we like to write as just AB without a line above it. If there is a line above it, obviously we know that that's talking about the type of line that AB is. But if you just see the letters AB next to each other, that's talking about the distance, or how long segment AB is. The distance between points A and B is the absolute value of the difference between their coordinates. The distance between points A and B, written as AB, is the absolute value of the difference between their coordinates. That is incredibly, incredibly wordy. The formula is also going to look a little bit long, but the process for using the formula is very simple. The distance between points A and B, which we write as AB, is equal to, we want to use the absolute value here. For those who don't remember absolute value is a function that turns whatever is inside of it positive. It's the absolute value of A minus B, because it's the difference between their coordinates, and difference means minus. Oh boy. Let's see if we can do this in action. For the example, let's say we have a number line that stretches on and on and on for a long time. I'm putting 3 dots to show that it continues off in both directions very far. Let's say we've got the number -17 here and the number 43 here, and we're trying to figure out the distance between those two. Well, according to this formula, the distance between these 2 points, A and B, is just the absolute value of A. We didn't really pick a point A. I'll pick -17 as point A, minus point B, or the coordinates of point B. So this is the absolute value of -17 minus 43. -17 minus another 43 is just -60. And the absolute value of -60 is just 60. This would be the distance between negative 17 and 43. They're 60 spaces apart. The reason why we use absolute value in this is because distances can't be negative. I mean, there's no way to walk negative 2 miles. So the absolute value just guarantees that whenever we get a negative, we just make it positive. Almost done with the definitions. These two are pretty simple. A construction is just a geometric drawing made with simple tools. We've been doing those for our warm-ups every day. And the word congruent has a formal definition here, but I want to let you know that the simplest way I can explain it is the same. But Mr. Strager, don't we already have a word for the same? We use the word equals. Well, yes, we do use the word equals, but there is a difference. When we say something is equal to something else, we are talking about their values. 2 is equal to 2. 8 divided by 4 is equal to 2. 16 squared is equal to 256. Equals is a sign that shows something's value. But the congruency symbol looks like this and is referring to two shapes, two geometric figures. So for example, you could say that the lengths of some line segments, line segment AB and line segment CD, which we have shown down here below, are the same. I mean, look at them. One of them is 10 centimeters, the other is 10 centimeters. So we can say that line segment AB has the same length as line segment CD. But if we wanted to talk more in depth about the actual shapes, the way that they're drawn, the fact that they're both line segments, all of this is to say that they are congruent. We could also say that line segment AB, with that little line above it for line segment, is congruent to line segment CD. For something like this, the difference isn't very easy to see, but just remember, the equal sign is shown whenever we want to talk about numbers. The congruency symbol is shown anytime we want to talk about shapes being the same. Of course, we want a more shorthand way of showing that something is congruent. So we have something called tick marks. Tick marks are small markings made on line segments, and other things too, to show that they are the same. We're going to be using these for angles as well a little bit later, but like I said, that's going to come at a later time. These tick marks can really be anything. Here, they're triangles. Here, we've got a couple of them that are lines, and a couple of them that are circles. Tick marks show that two sides with the same tick mark are congruent. So, for instance, that these two sides are the same, but that these longer two are different from the original two. Before we can talk about labeling congruent segments, we need to first talk about something that's a little bit inconvenient for us. Believe it or not, the order does matter when labeling congruent segments, and it's not so easy as just looking at the shapes and saying that side equals that side. I mean, really, if we're looking at these shapes, it's pretty clear to see that in triangle AB, there's a single tick mark, and in triangle in triangle ABC, we have this length. In triangle DEF, we have this length. They're the same. What's the big deal? Well, the big deal is that the way we write the order of our points does matter. Let's say, for instance, we started to write out the congruency statement. AB, or line segment AB, is congruent to and we wanted to finish this statement. How do we know whether it's DF or FD? Like I said, the order does matter, so we have to get it right. The way to get it right is to take a look at the first letter of your first segment. We have the letter A. We now need to figure out what point in the second figure corresponds to point A, or is the same. Well, it's a little bit tricky, but we notice that point A has a dash tick mark on its right side, if you were to look at it upside down. If you want to look at it like this, we could say it's on its left side. And a rhombus shape on its right side. It has a tick on the left and a rhombus on the right. So when looking at this diagram, we're looking for the point that has a tick on its left and a rhombus on its right. Well, there's only one point that does that, and that's actually, if we flip this page upside down, point F. Point F has a tick mark on its left side and a rhombus on its right. A and F are what we would call corresponding points. When labeling congruent segments, corresponding points should be in the same order. So if A was the first one in our first segment, F should be the first one in our second segment. And similarly, we can do the same thing for point B. Point B here has this line this line above it, and this square to the right of it. If I rotate this paper, we can see that, oh, point D has a line tick mark and a square next to it. So B corresponds to D. That's why we write in D. There are a lot of ways to check if two points are congruent. The easiest way, though, is to look at their tick marks. So with that, I want you to pause the video and try to see if you can come up with a congruent statement in the correct order between AC, line segment AC, and something else. Pause the video and see if you can do it. Hopefully you've had a chance to try it out. Let's take a look. We already said that point A corresponds to point F, so obviously this is going to have to be point F. And we already have all these other points being congruent. It's not crazy to say that point C and point E should also be corresponding. So if we have AC, we should have FE. The last congruent segment here starts with BC, or you could do CB. The first one doesn't really matter the order. What matters is that your second segment matches the order you chose. Since BC starts with B, we know that B corresponds to D. Our next line segment should start with D and go towards E. It should be DE. Those are congruent segments. On example 7, we're asked to now label some congruent statements. And here's a little bit of a challenge for those of you who are looking closely. There is actually a typo in these congruent statements. Not one that changes our diagrams that we're going to draw, but one that is technically not correct because corresponding points aren't written in the same spot. Either way, we are now tasked with labeling the diagram with some congruent statements. We see that line segment AB is congruent to line segment IJ in the second trapezoid. So we need to come up with a tick marking. Old reliable is just to use a single tick mark, AB, and it has to be congruent to IJ, so we're going to put the same tick mark on that side. That shows that those two line segments are congruent. Next we have line segment AD and line segment IH. Well, we already used one tick mark. Let's use, two tick marks. If AD is congruent to IH, we should have it go like this. Next up, we have CB is congruent to KJ. So we can go with 3 tick marks, but it's starting to get a little bit hectic here. But 3 tick marks is good old reliable. CB is congruent to KJ, like so. And last but not least, CD should be congruent to KH. Well, we could use 4 tick marks, but I want to remind you that you can use whatever you want for these tick marks. I'm actually not going to use 4 just because it's a little bit much. I'm going to use an arrowhead. Does that sound pretty reasonable? I think an arrowhead sounds perfect. There we go. Now we have labeled the diagram with the congruencies. Let's flip the page and go on to the next part of our notes. Right here. Now, this is the part of the class where I have to remind you, a ruler is absolutely required. We won't be using it every day or anything, but we will be using it pretty frequently. So, the ruler postulate. This is another postulate, so we know that it's going to be sort of an obvious fact. It doesn't need explaining. But here's the basics of the ruler postulate. If you have an accurate ruler, like this, and you know those measurements are accurate, you can use that ruler to measure something else. The ruler postulate just says, if you have a very good measuring stick, you can measure with it. Thank you, ruler postulate. We needed that. To measure something using a ruler, we have to be very careful. You see how these dots here are relatively large? Normally, they won't look like that. Normally, you'll be dealing with a much, much smaller set of lines. I'll give you an example from the homework so you can see it. You're going to mostly be dealing with lines that look like this. It's very easy to accurately measure a line that has these tiny endpoints because you know exactly where to place the ruler. But where should I place the ruler on this one? Should I try to aim for the center of the dot? Should I try to move it to the left or to the right of the dot? It's sort of tough to tell. My recommendation, and what I'm going to choose to do, is I'm actually going to put it to the start of the dot, right here. That seems pretty accurate. And on the other side, I'm going to measure it to the start of the next dot. So, measuring it from start of dot to start of dot, it looks like I've got a pretty good sense of the measurement. And I apologize, on the camera it's very hard to see how accurate this dot is. Rest assured, it is at the edge of the dot, even though the camera will make it look different because of the bending of the light. According to this ruler, this here, this segment, is where we should measure. Uh-oh, it's not a whole number. How on earth can we understand this? Well, allow me to give you a little bit of a guide for how to use an inch ruler. It's definitely not the most optimal ruler type to use, but it's the one we've got. So let's say I've got my 3-inch mark here. 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And I've got my 4-inch mark right over here. And I want to see what these middle marks are going to be on the ruler. The one directly in the middle, between the 3 and the 4, should be plenty obvious. The mark between the 3 and the 4 on the ruler is halfway between, so it should be 3 1/2, or 3.5. And it continues in this sort of pattern for the other tick marks too. We cut a segment in half, like so, or like so, and then the measurement gets cut in half. So instead of 3 1/2, this is 3 1/4, or 3.25. So what's this going to be? Well, we can actually count up by quarters to get there. So 3 0/4, 3 1/4. 3 2/4 is the same as 3 1/2. 2/4 is 1/2. So this must be 3 3/4, or 3.75. Let's keep it going. Let's get a little bit smaller. The next tick marks are halfway between 3 and 3 1/4. So we know it's going to be 3 1/8, or 3.125. And we could just count up by eighths. 3 1/8, 3 2/8. This will be 3 3/8, which is 3.375. Sorry, no, that is correct. 3.375. I had a brain fart. 3 4/8 is right in the middle, because 4/8 is a half. So this must be 3 5/8, which is 3.625. 3 6/8 is 3.75. And 3 7/8 is going to give us 3.875. But of course, there is one layer deeper. I'm not going to give the decimal measurements for these ones because it'll just take up too much of your time. I don't want to waste your time here. I just want to make sure we're all in the know. These are the 16th markers. So 3 1/16. 3 2/16 is here. 3 3/16. And so on and so forth. You get the picture. On my ruler, I had measured it precisely to this point here. So let's figure out what type of measurement it is. It's not a half, because a half marker is right here. It's not a quarter, because the quarter marker is here. But it's in between 1/4 and 1/2. Well, we know it's going to be an eighth tick marker, but how many eighths? Well, we count the same level of tick marks. 1/8, 2/8 is a quarter. This is 3/8. So this is 3 3/8 inches, or 3.375. If we want to do centimeters, centimeters is a lot easier, actually. For centimeters, it's always just going to be, every tick mark is 1/10 of a centimeter. So if I'm looking at this, I'm going to measure that as approximately, let's call that 8.5, just because that's a very safe number to go to. Obviously, this may not be the most accurate possible measurement for it, but it's the measurement I got here. 8.5 is something I can be happy with. Try to measure the next segment by pausing the video and giving it a shot. Here's what I got for my measurements. Check to see if yours were close. Again, I'm not the absolute authority on measurement. This ruler is an old wooden ruler that I've had for a very long time, and it could very easily have warped or shifted as time went on. So it's okay if you're slightly different than mine. It doesn't mean that you're wrong, doesn't mean that I'm wrong. One thing that we can both agree on is the definition of between, though. We know what between means normally, but in geometry we have a very specific definition. Again, because we need to be super specific to see what counts and what doesn't. When 3 points are collinear, you can say that one point is between the other two. So a point is between another point if 3 points, and this could be more than 3 points as well, but at least 3 points are collinear with one on each side. That's what it means to be between. B is in between A and C. But if I asked you, is F in between D and E? If I asked somebody on the street, is F between D and E, they would say, why are you asking that on the street? But they would also probably say, yeah, it looks like it's in between. We know as geometry students, this only works if F is on the line. So be very specific. All right, now for the meat and potatoes of this lesson. We are going to learn a postulate that is very crucial. It's also very self-explanatory, but very crucial. Let me give you this. I have a marker here. I'm going to zoom out so we can see this. The marker is 5 centimeters, and it's a line segment, right? It has a start and an end point. Let's call this segment AB. This marker is now segment AB. We all know how long this ruler is. It literally has the measurements on it for us. This ruler is 12 inches long. Let's call this line segment, again, because it has two ends. Let's call this one line segment BC. If I was to superglue my beautiful 5-inch long marker to this fantastic 12-inch long ruler, you wouldn't be able to see the end of it because it stretches off the camera. But we could very accurately say, yes, this should be 17 inches long. Why? Well, because we're adding one segment to another by the endpoints. This is the segment addition postulate. The segment addition postulate says, if you have one line segment and you add on another line segment by combining an endpoint, the longer line segment that you just created has a length of the first plus the second. Formulaically, we write this as AB, so the length of line segment AB, plus BC, the length of line segment BC, is going to actually equal the length of the entire line segment. AC, the larger line segment. This also works backwards. If AB plus BC is AC, then that means that B must be between A and C. So let's take some examples and see if we can do them. Example 1 is, two friends leave their homes and walk in a straight line towards each other's home. Stop right away. I think the best way to do word problems and just general problems that involve, figures like this is to draw them out. So I'm actually going to draw these two friends' homes. Here we go. This is a nice little country home there. And over here, let's say the second friend lives in a condo. It's funny because they both look the same. Over here, we basically have a starting point and an ending point. Let's call the starting point point A and the ending point point C. For no reason in particular. They're walking in a straight line towards each other's houses, so we know it's going to be along that path. When they meet, one has walked 425 yards, the other has walked 267 yards. Friend 2 is slacking. So they don't meet in the exact middle, but they do meet near the middle. We'll say that's pretty good. We want to figure out how far apart their homes are. First thing is, let's call the meeting place B so that we can use our formula. Our formula says the first segment plus the second segment will equal the whole segment. So if AB plus BC equals AC, then all we need to do is figure out how long AB and BC are, and we'll figure out how long the total distance is, or how far apart their homes are. So, AC in this particular problem is unknown. And what do we use to represent unknowns? We use variables. So let's say that the length of AC here is just x, an unknown. But we do know AB's length should be 425 yards, because that's how far friend A walked. And we know that BC should be 267 yards. That's how far friend B walked. So 425 plus 267 is going to equal x. That means that x, the total distance, which we call AC, is 692 yards. Perfect. Done. This type of problem is easy because we just need to add together the two segments that we know. But let's see what happens if there's a segment that we don't know, like example 2. In example 2, there is a car which I am going to beautifully draw because I am the best artist in the world. So here is the car that we can draw, and we have a trailer attached to it. I'm just going to draw that as a large rectangle just for simplicity's sake. A car with a trailer has a total length of 27 feet. So this time we're not given just the individual segments. We're told that the entire thing is 27. There we go. This entire thing, which I'm going to call AC, again, because it's what we're used to, is 27 feet long. I'm going to use this curly bracket to denote that these two together will make 27. And we'll call that 27 feet. And we also know that the trailer has a total length of 13 feet. So this dot here, where the car and the trailer meet, to the end of the trailer, is 13 feet. And we're trying to figure out how long the car is this time. So we know the total, we're trying to figure out one of the line segments. If we don't know the length of this line segment, if that's what we're trying to solve for, we're going to call it x. Once again, we can use our segment addition postulate. AB plus BC, again, AB being the first segment that we labeled, BC being the second segment that we labeled, we don't need to use those letters, but I like using them, equals AC. So now we just need to fill in the parts that we know. We know that AB is our unknown, so let's call that x. We know that BC is the length of the trailer, that's 13 feet, and AC is the name we gave to the car plus trailer, which is 27. How can we solve that one? Well, it's really quick. We can just subtract 13 from both sides, canceling those out, and getting x, which is line segment AB this time, is equal to 14 feet. Done. The car is 14 feet long. Finally, we are on example 3, and this is going to be where we put it all to the test. This time, there's no abstract word, or there's no concrete word problem. This is an abstract one. Suppose that M is between L and N. We can assume that M, L, and N are points, because we've been dealing with points this entire time. Although technically I suppose they could also be planes, but we're not working with planes. We know that they're points. I don't know where M is going to be in between. It just says that M is between. So, I'm going to give you this warning now. This drawing is not going to be accurate proportionally. There's no way to know where it could be. If there's no way to know where it could be, I'm going to put it around the middle. But again, this is not going to be proportionately accurate. In this particular problem, actually, one side is way longer than the other. Or one segment, I should say. We want to use the segment addition postulate to solve for the variable. And I'm going to call these pieces L, M, and N. Then, after we solve for a variable, we want to find Lm and Mn's length. This time, we're given full equations for the lengths. So we're told that Lm has a length of 3x plus 8. We don't know what x is yet. That's what we're trying to solve for. Mn also has a length in terms of x. It's 2x minus 5. If this was the information that we were given right now, there would be no possible way to figure out what x is or the lengths of either of these two. But we are given the total length. Ln is 23. So I'm going to draw my curly little bracket here and call it 23. Once again, we have to use the segment addition postulate to help us. I mean, our first segment is Lm, so let's call that just Lm. Our second segment looks like it's Mn. And our third segment, the segment that is the long one that's created, is ln. So when we try to do math with these segments, we know that we can just add together the first plus the second to equal this mystical 23. So we get ln is just 3x plus 8 plus mn, which is 2x minus 5, equals 23. This is just an Algebra 1 problem now. We know that we should start by combining our like terms. 3x and 2x combine to make 5x. 8 plus negative 5 will give us positive 3. And our 23 sticks around. Some of you may have noticed what we do next, which is subtract 3 from both sides, because reverse PEMDAS tells us we have to do it in that order. When we subtract these, we get 5x equals 20. And then we just need to divide both sides by 5 to get x. X, in this case, equals 4. We have just solved the hardest part of this problem, finding x. X is 4. But we're not quite done yet, because you see, we don't just want x, we want the lengths of these segments. Well, we started off by knowing that 3x plus 8 was the first segment, segment LM. So if we know x is 4, we can just plug 4 in to the equation here, or to the expression. 3 times 4 plus 8 will be the length of that segment, which is 3 times 4 is 12, plus 8 is 20. LM has a length of 20. I am going to show what happens when you plug in x for the second line segment, but there is a much easier way of finding the second line segment. If we have 2x minus 5 as the second line segment, we know that we can just substitute in 4 for x, since we solved and found that x is 4. 2 times 4 minus 5, 2 times 4 is 8, 8 minus 5 is 3. So that's our second line segment. The much easier way to find that second line segment, we can use the segment addition postulate again. If the first segment is 20, 20 plus the second one has to equal 23. So by the segment addition postulate, 20 plus 3 equals 23. See, it's everywhere. That concludes our notes for today. Thank you so much, everybody. Have a fantastic rest of your day.